everybody get a copy of the notes and the homework assignment? Looks like I've got all of your assignments. So like the previous one, the next assignment is only 2 problems. And maybe similar level of difficulty, maybe a little harder on problem 42. No, the handout one is actually, the handout problem I think is the more challenging of the 2. But today we're going to go over the Nodal method, which will allow you to solve problem 42 from the book, which is 3 pipelines. And so we'll get into all of that. We're not having a quiz today, but, yeah, all right. Significant cough. So just to review what we did with the 3 reservoir problem, you assume some head value at D. And it's important to emphasize that the head at D is different from the elevation at D. So the head at D is it's the elevation plus the pressure head plus the velocity head. And velocity head we can kind of justify ignoring, particularly because if there's 3 different diameter pipes at the junction, how do you know which velocity to use? I mean, it turns out that the average of the 3 velocities is probably the right approach. Just average the 3 velocities and find the velocity head there. But more than one student was a bit confused on the homework problem because it told you the elevation to the junction, but that wasn't the head. The elevation and the head are 2 separate things. Yeah. Well, because the water at the junction is really moving, but generally speaking, velocity head is small relative to the magnitude of the pressure head or the elevation head. So if we're wanting to be really precise, we include it, but sometimes we'll ignore it. In the case of the homework, I think that one of the velocities was up around, was it 11 meters per second? 8 or 9 meters per second. So that's actually getting high enough that it's better if we do include it, but I won't deduct points if you neglected the velocity head at the junction. And as I mentioned earlier, it's because you're optimizing both the head at D and the F that you can't just goal seek right from the beginning.
How would you get to the out minus the in?
So what you probably do, since there's 3 different pipe diameters, just find the average velocity for the 3 pipes. So if this one was 8 meters per second, and this was 7 meters per second, and this was 6 meters per second, just say, well, at the junction, let's say the average of these 3 is 7 meters per second. Because, you know, if you zoom in on what that junction looks like, it's looking like this. So you've got the water coming in here, the water coming in there, the water exiting. So what's the velocity head at a junction? And it's a matter of some debate. It is going to reduce the total pressure there because there is some movement in the flow, but we don't know exactly which pipe velocity to use. So my suggestion is just to average them.
So on that second homework problem, it asked pressure at D.
Yeah.
Do you not have to have another reference? Like,
You do have to keep track of Z.
Okay.
Yeah. I'm not saying ignore the elevation.
Well, no, I was saying like I did my A to D. Was I used one side was A, one side was D. Did you just need to use that formula?
I don't understand what you mean one side was A. The energy equation, right.
Yeah.
Mm-hmm.
Like I just saw where you left like the second part of it off. So you would use H of F.
Through the pipe from the reservoir. So you know the head at the reservoir because it's just the elevation. So you subtract the head losses, and then you can find the total head at D. And then what I'm saying is if you know the total head at D, which you calculated in the first part of the problem, what's the total head at D? Break it up into its components. The elevation, you know how high that junction is above the datum, so you subtract that from the head. And then you can subtract the velocity head, and then what's left over is the pressure head. And so whatever head is left, multiply that by gamma, and it gives you the pressure. This is a great typical problem for exams, quizzes, fundamentals of engineering. You know, this is kind of like a classic thing. It's a classic problem. And as it was mentioned in the recorded demo, the way you know that you've converged is that the F values aren't changing from iteration to iteration. You know, you've got multiple blocks of these calculations repeated. And when the F value has stabilized, and by stabilized I mean like within 1% from iteration to iteration, and when the flow in equals the flow out, that's when you know you can quit. And there were some instances where you can get flow in to equal flow out, but it's the wrong flow rates if the F values aren't correct yet. And that's why you have to paste multiple iterations, is that you could possibly find some theoretical head value that gives you flow in equals flow out, but if you haven't yet nailed down the correct F values, then the actual flow rates wouldn't be correct, even if in equaled out. So you got to be a little bit cautious. And convergence criteria is going to be an important thing when we get into the Hardy-Cross method starting on Thursday as well. All right, so this is the Moody diagram taken from your textbook. And I wanted to point out a couple of things about the Moody diagram. Of course, the first is that in really low Reynolds number, that the F value is 64 divided by the Reynolds number. So it's a linear curve that's very easy to calculate. Now here's another thing. It says smooth pipes. A smooth pipe is something that is essentially without roughness because of the material. And typical material that they classify as smooth would be glass tubing or maybe drawn copper tubing. Just the material itself is so smooth that if you want to calculate the F value, you just find the Reynolds number, go up to the smooth pipes, and over. That's a smooth pipe. Now for everything else, things that do have an equivalent sand roughness, epsilon, and you know the diameter of the pipe, we've talked before about how you can use the Moody diagram by going to the Reynolds number, over, and calculate, and finding the F. But you'll notice that there's this dashed line. And graphically speaking, what's going on with this dashed line is that to the left of the dashed line, F value depends on Reynolds number. Like a low Reynolds number is going to take you up here, but a high Reynolds number would take you lower. But past this dashed line, and it looks like it doesn't matter what Reynolds number you've got, it's going to be the same F value. So in other words, the F value is unaffected by further increases in velocity. That's what we call fully turbulent flow. And the implication of fully turbulent flow is that it changes the equation we'd use to find F. You know, if we're thinking about the Jane equation, if we've got a really big Reynolds number, remember I've mentioned this before, if you've got a really big Reynolds number, that makes this term insignificant because Reynolds number is in the denominator. So for a very large Reynolds number, the F value only depends on K sub S to D. And so the F value in the Moody diagram only depends on the relative roughness when you get past that dashed line, which represents the threshold into fully turbulent flow. So if fully turbulent, you can rearrange the Jane equation to look a little bit simpler. And sometimes that's a useful place to start in your initial guess of the F value. So think about the assignment you've just completed. Maybe your initial F value, you just guessed 0.02 because it's like in the middle of the road. You'd have a smarter guess if instead of just picking that number, if you use this. Because you don't know the Reynolds number yet, but you can do better than just a random guess because you can put in the K sub S for the material that it is and the diameter of the pipe. And so this fully turbulent assumption is something that can help you when you're having to make all these assumptions at once to make a better assumption your first time around. And then once you find the actual flow rate, then you can check the fully turbulent assumption to see if it's reasonable or to calculate an updated and an improved F value using the full Jane equation or the full Colebrook equation. So think about in this lower expression, this is the Colebrook equation, think about how the Colebrook equation changes if you've got a really big Reynolds number, then this whole term gets canceled out. So once again, you've got an explicit equation. It's no longer implicit where the F value is on both sides of that equation. So it becomes easy to solve, relatively easy to solve, if we assume that the water's moving so fast that it's in this range. And a lot of the time the fully turbulent assumption is valid, and even when it's not valid, it's a better place to start than a random guess. Any questions about what fully turbulent means? All right, so this is what we're doing today. It's called the Nodal method. And it's called the Nodal method because we're going to examine pipe junctions, or a node, relative to the continuity equation. Remember, the continuity equation says whatever comes in to a junction has to go out of a junction if there's no capacity for storage. And so these little dashed lines here represent a control volume. And if we analyze the control volume, there's no reservoir here. We don't see a reservoir. So whatever the flow rate from Y and X is coming together, both of those flows are going to enter pipe Z. And so Q sub Z will be equal to Q sub X plus Q sub Y. We're going to be applying this very simple process to solve some kind of, it's like an interesting question. Another one of these classic quiz, exam, or FE type questions is the classic nodal method problem that I'll show you in just a minute. The application is, let's say that you know water is flowing through a pipe. You know the flow rate. But then it splits in two different directions. It's going to come together later, but how much of the flow goes through the top pipe versus the bottom pipe? And this could either be a side view or a top view. That's not really the relevant part. What's relevant is, how do you know how much of the flow goes through each of the two pipes? And so let's just step through some ideas here in the next slide and see if you know, relatively speaking, which flow is going to be greater, pipe B or pipe C. When you're able to say what the flow through one of the pipes is, then obviously you can say what the flow through the other one is. Because if you know A and you know C, therefore you will know B, just by subtraction. And vice versa. If you knew the flow rate through B, then you could find the flow rate through C. And so this is just rearranging the continuity equation to find either one of the flow rates when you know the other. Okay, so let's say we've got this classic pipe network with pipe splitting and then rejoining, and keeping in mind the Darcy-Weisbach equation. The Darcy-Weisbach equation says that the head loss due to pipe friction depends on the roughness of the pipe, which is expressed by the F value, the length of the pipe, and the velocity squared, divided by the diameter times 2 times G. Okay, so that tells you how much head loss there is. Now let's say that both of the pipe lengths are the same, they're the same diameter, and they're made out of the same stuff. So the F value is the same. So which of the two flows will be greater? Q sub B or Q sub C?
Is there elevation difference?
There's no elevation difference. And I'll tell you, even if there was, it wouldn't matter. It would be the same. Why do you say that? Yeah. All right. That's a big part of it, yeah. Water takes the path of least resistance. What does that mean?
It means like if, you wouldn't have more flow in one pipe, you'd have more head loss in
Yeah,
one pipe. So
right.
it would just go to the other pipe.
Okay, so yeah, think about the decision the water is going to make as it comes to the pipe. Now, water doesn't think, right? Let's say theoretically, the water wants to go the easiest path, and I think people do the same thing sometimes. I know I do. Okay, so the water is looking for what's the easiest path. Well, the two paths are identical. They've got the same diameter, they've got the same length, the same roughness. The pipe is looking for how can I get down here with the least head loss? That's what it's looking for. The water is looking for the path that's going to cause the least head loss, the easiest path. And if the two paths are the same, some of the particles will go to the left, some of the particles will go to the right. It doesn't matter. It'll be equal. So if everything's the same, the flows are equal. Okay, so with that reasoning, what if the following. Diameter's the same, length's the same, but now pipe B, which is this one on top, is more rough than pipe C. So it has maybe a material that's got a larger equivalent sand roughness. So what do you think is going to happen here? Is it going to be all or nothing? Will all of the water go through one of the pipes? Will some of it? Will it be equal again? Gil, what do you think? Okay, so which one is going to have more flow? Okay, so B is going to have less flow than C, and that's right. It's not that the water will entirely go one direction or the other, but it'll come into an equilibrium where it doesn't matter which path it goes because there's the same head loss through both routes. All right, so what if the diameter at C is bigger than the diameter of B? So the change is the pipe diameter size. Pipe C will take more flow. Speaking in terms of the Darcy-Weisbach, why is that? Why would pipe C take more flow? Can you express that in terms of this equation? Okay, so a bigger diameter is going to mean that there's less head loss, and also a bigger diameter is going to mean there's less velocity too. And so both of those things, big diameter, less velocity, makes that route more advantageous because there's more energy loss. Less energy loss. All right. So everybody, I think, is starting to get a feel for how things work. Water goes through the path of least resistance. Now, what about this one? The diameter of B is bigger, so that would tell us more water will go through B. But the length of B is larger. Now, the one with greater length has more resistance, right? Because it's got the longer flow path. And then pipe C is more rough. So what will happen here? Well, the thing is it's unclear because we don't know how much longer it is. Maybe it's 1 foot longer, which would mean it's not that much of a bigger deal as far as B versus C. But then what if the diameters are triple, you know? Or what if the roughness is a matter of a glass pipe versus a concrete pipe? So it's indeterminate at this point. And so we have to have some sort of a procedure that will allow us to calculate what is the relative magnitude of flows when we have a variety of factors that are quantified. You know, a whole range of diameters, lengths, roughness values. So here's what we know. That the head loss through both of the paths is equal. And that's how you solve these problems, is that the head at the first junction, there's some value. There's a certain amount of head there, maybe 20 meters of head here, just for example. And when it gets to the downstream node, there's going to be less head. So maybe it had 20 meters of head here, and by the time it gets here, there will be 10 meters. But the key thing is it doesn't matter whether you go through the top or through the bottom pipe, you end up at the same head value. It's like walking down a mountain. If you're walking down a mountain straight down the hill, eventually you're going to get to the same elevation as whoever goes through a winding path. It's different paths, but the same change in energy from beginning to end. And so what we're going to, the expression that if we expand out the definition for H sub F, you know, here's the Darcy-Weisbach equation, we can set the two equal to each other. And that's how you find out what the relative velocities are. Is you substitute in what's the F value, what's the length, what's the diameter. Everything here will be defined except for the velocity. Everything will be fixed in a problem like this. And really what we're going to be trying to find out is how much of the flow goes through one pipe versus another. And so the unknown will be the velocity. And we'll have two unknowns, right? We'll know V sub B is going to be unknown, and so is V sub C. So this one equation has two unknowns. So what do we need in order to be able to solve the situation if we've got one equation with two unknowns? We need another equation. Do we have another equation? Which one do we have? You knew. You've got hope. There's got to be another equation. That's true. That's true. We don't go over mysteries here. We go over solutions. And the other equation is the continuity equation. That's the one that's going to allow us to solve the nodal question. All right. So just to reiterate, it doesn't matter how you get from point 1 to point 2, from the upstream to the downstream junction, through the top or the bottom pipe, but the total head loss through each of the pipes is equal. And that's why we set the Darcy-Weisbach equation at 1 through one pipe equal to the Darcy-Weisbach equation through the other. All right, so that was a simple concept. And so I go from a simple concept to showing you this scary equation. It looks kind of ugly, but if you look at it long enough, what you realize is, oh, that's just the energy equation. That's just the energy equation that's being rewritten a certain way for a certain reason. So H, what I mean by H is pressure head, elevation, and velocity head. That's what I mean by H. Okay, so if it's all of these at 1, minus H sub f plus H sub p is equal to H2. And then what we usually do is the energy equation is we move the friction term from the left side over here, plus H sub f. So it's a lot less scary now. This is our old friend, the energy equation. It's here a little bit differently, and remember that one of the things that we sometimes do is that instead of saying FLV squared divided by D2G is H sub f, well, if we don't know the velocity, sometimes it's useful to say instead FLQ squared divided by D2GA squared. So that's why it's got this Q times absolute value of Q divided by 2GA squared. So that's just the velocity head term. And remember that velocity head comes into play for both friction losses and local losses. And those are both terms that are shown here. FLD, this is the friction term that's going to be multiplied by the velocity head. And then this sum of the K sub 0, that's local losses. Okay, so this is just energy loss. And then Q divided by absolute value of Q, that's for reasons of direction. Because what we always assume is that water goes from 1 to 2. So we're always going to be applying this with that assumption, but sometimes we'll apply this equation when we're not sure what direction the water's flowing. We'll have to be maybe solving loop problems, like water comes in and then it goes out. Sometimes we won't know if the water is going like this, and actually that might happen. It seems stupid that it would go circular, but it might happen. Sometimes there are ambiguities in flow direction, and so this Q times the absolute value of Q is going to be a tool we use starting Thursday in order to correct if we've made the wrong assumption for flow direction. It's not going to come into play in today's example, but I wanted to let you know where it's coming from. So here's all of the descriptions, and they go into a little bit more detail in your book if you want to look at that. But the thing I want to emphasize is 1 is upstream and 2 is downstream. We assume water goes from 1 towards 2 when we're applying the nodal method.
I would say H2, this is just the energy equation.
Yeah.
CF.
No, this is the energy equation. I just did it right over here.
I know, but please wave the magic wand.
All right, well, let me wave harder. H1.
Okay.
All right. And then here's H2. So imagine H2 is over there, and H1 is on the other side. Okay, so plus HF. H1, H sub F goes over with the H1 term. So that's why it's minus, and then there's the H sub P. So a little more waving. Sometimes it's all it takes.
Backwards, that's fine.
Yeah, yeah. Okay. So the way you solve the nodal method problem is you can find the total head at 1. And in problems like this, you'll often be given the elevation at 1 and the diameter of the pipes. You can find the velocity head, and you'll find the total head at 1 by adding up the 3 terms that goes into head. And then you'll find the head at 2 in terms of Q sub B, the head at 2 in terms of QC, and then you set the 2 terms equal to each other. Now that's if you're actually trying to find what is the head at 2. Sometimes you just need to find what's the flow rate, and you don't care what the pressure is downstream. You just want to find out how much of the flow goes through each of the 2 pipes. And so I'll show you both of those approaches. The shortcut you can use if the only thing you care about is the relative flow rates. You can take a little bit of a shortcut. Okay, so in this example, what we're looking at is a pipe that splits. The water at 3 cubic meters per second is going through this pipe 1. Pipe 1 has a certain diameter, a certain given length. And so with the diameter, I've already calculated the area just to save some time. And I calculated the velocity by Q divided by A. We know that all of these pipes are galvanized iron. And so the K sub S relative to D, we know from this K sub S divided by the diameter. And so just to start things off, what we need to do is assume fully turbulent in order to calculate the F value for pipe 3, because we don't know what the flow rate is, and so we wouldn't necessarily be able to calculate the F value otherwise. And so this F value is based on the fully turbulent assumption. We are also in the problem statement here given the elevation at all 3 of the points, at location A, B, C, and D. So there's 2 things that we're going to be doing in this example. First of all, finding out the flow through the 2 pipes where right now it's not defined. And then secondly, we're going to find the pressure at D. Okay, so just before we get into the number crunching, think qualitatively. Just based on logic, which of the 2 pipes do you think is going to have more flow? Can we do that same thing that we did before where we were just trying to feel it out? They're both made out of the same material, so F doesn't matter. One of them is longer, and the longer one also has a smaller diameter. So Zach said he thinks more flow is going to go through pipe 2, and I agree. Just by looking at it, we can tell that Q2 should be greater than Q3 because it's got a bigger diameter and it's shorter. Does everybody feel good about that? All right. Well, what I'd like you to do, just to kick things off, is calculate the F value that we should use for pipe 3 using the fully turbulent flow assumption. Assume that the flow is fully turbulent and find F. Okay, so we set the Darcy-Weisbach equation at 2 equal to all of those terms at 3. And so we can substitute in the known values, or let's say that we want to find what is the velocity in pipe 2. So the velocity in pipe 2 is going to be D2, 2G, F3, L3, V3 squared divided by F2, L2, D3, 2G, and all of that is the square root. So I'm just solving for V2. So I moved all of those terms over to the numerator that were in the denominator on this side, and all the terms that were in the numerator on this side to the denominator over there. I can cancel out 2G, and so now if I make the numerical substitution, I've got the diameter 2 is 0.5 meters. The F value at 3, 0.0157. And the length of 3 was 550 meters. And then that's V3 squared. Oh, just barely made it. And now in the denominator, I've got 0.0149 0.500 was the length through pipe 2, and then 0.4 meters is diameter 3. And then all of this is to the 1/2 power. Raise the screen so you can see that. Okay, so if I simplify that, it's V2 is 1.204 V3. So the velocity through pipe 2 is going to be greater than the velocity through pipe 3, is what this is saying. Okay, if you have a question up to this point, now's the time to ask, because we're about to apply this into the continuity equation. So any questions so far on how or why we did what we did? Exactly, yeah. We didn't actually consider the pressures at all yet, remember. All we are saying is we know that water is going to go through whatever path is easiest, whatever flow path is most advantageous to it. And so based on the relative length, the relative diameter, the roughness, we know that this is going to be the ratio of the velocities. All right, so where we can apply this now is into the continuity equation. And the continuity equation tells us that the Q total, which is 3 cubic meters per second, that's going to be A2 V2 plus A3 V3. So the water that's flowing through pipe 1 is going to split at junction B. Some of it's going to go through pipe 2, some of it's going to go through pipe 3, but altogether the flow is still going to equal 3 cubic meters per second. Well, we already know the cross-sectional areas, and we know the ratio of the velocities, and so this problem's all but solved. We can substitute those in. We've got 0.1963 is the area of pipe 2, and then we know that the velocity in pipe 2 is 1.204 V3. And so instead of saying V2, that wouldn't do me any good because I'd still have two unknowns. Instead of saying V2, I substituted in what I know the relationship between V2 and V3 is. So I'm going to be solving this for V3. Plus A3, which is 1257 square meters times V3, and all of that's going to be equal to 3 cubic meters per second. Okay, so this works out to 0.2363 V3 plus 0.1257 V3 is equal to 3. And so that is going to give us that V3 is 8.29 meters per second. And so therefore V2, which is 1.204 V3, will be equal to 9.98 meters per second. Just again using that ratio that we found by equating the head loss through each route. Okay, so Q3 will be V3A3. So that is the 8.29 meters per second times the cross-sectional area of pipe 3, 0.1257 square meters. So Q3 is 1.042 cubic meters per second. And the flow through pipe 2 is going to be A2 V2. And that is the area of 0.1963 meters squared. The velocity through that pipe was 9.98 meters per second. And that works out to 1.9 0.59 cubic meters per second. So does it make sense? First of all, the first check of whether it makes sense is that those two things should equal 3. It should add up to be 3. And it does. The second thing is, remember we said qualitatively, just by looking at the situation, we think that more flow should be going through pipe 2, because pipe 2 had the larger diameter and the shorter length. And so is Q2 bigger than Q3? And it is. So, I mean, it seems to line up with what we were expecting originally. So we've solved the first part of this example problem, that is to find the flows. Any questions with that so far? Now, ordinarily, what we'd want to do now is check the validity of the fully turbulent flow assumption, because this F value and the F value we found was based on assuming the flow is fully turbulent. So let's check that, just out of good practice. Is the flow fully turbulent? And we can do that by saying the Reynolds number in pipe 2 is V2 D2 divided by the kinematic viscosity. So 9.98 meters per second times the diameter of 0.5 meters divided by the kinematic viscosity, 1 times 10 to the minus 6th meters squared per second. That's going to be 4.99 times 10 to the 6th is the Reynolds number in pipe 2. And the Reynolds number in pipe 3 is going to be 8.29 meters per second times the diameter of the pipe, which is 0.40 meters, divided by the kinematic viscosity, 1 times 10 to the minus 6th meters squared per second. And the Reynolds number is 3.316 times 10 to the 6th. So is it fully turbulent? We can check a couple of ways. We could go back to the Moody diagram and see what side of the line that's on. Here's the Moody diagram. It's a little small. Okay, so here we have a relative roughness of pipe for pipe 2. I have the relative roughness over here. For pipe 2 is 0.0003. So then let's go back to here. 0.0003. So it'd be over there. And it looks like actually we're on the left side, because we have a Reynolds number of 5 times 10 to the 6th, and so that puts us here. And if we go up to the 0.003 line, oh, we're just right on the border. So we could probably say, yeah, fully turbulent, fine, because if you go 5 times 10 to the 6th up, and then here is the 0.003, it's going to be in between there, and it really is just right on the border. So we slide under the radar, but I'm starting to feel a little nervous about pipe 3. Pipe 3 had a relative roughness of 0.000375. So we go over to here. 375 puts us a little bit higher. So we're over here. And the Reynolds number is 3 times 10 to the 6th. So that takes us, here's 3 times 10 to the 6th. Yeah, I don't think we're going to make it this time. We are not fully turbulent. It's still pretty flat. So what we need to do to be strictly correct about this is calculate the F value based on the Jane equation. So we'd go to now the full Jane equation, and we'd say that the F for pipe 3 is 1.325, and then the logarithm of 0.15 millimeters divided by 3.7 times 400 millimeters plus, now this time we're not going to neglect the the right term. We'll use the actual 5.74, the Reynolds number, which was 3.316 times 10 to the 6th, that to the 0.9 power, square it. The F value here is going to be 0.0159. Well, it didn't change a lot, did it? 0.0157, we have the 1.0159. So what would we need to do with our updated F value? We'd need to substitute them in here again and do everything a second time with better F values. I won't do that on the board because it wouldn't really add a lot of value, but that's the problem-solving process, is if you don't have a correct F value the first time through, you're going to get the wrong ratio of velocities. And the flow rate won't actually be what we calculated unless you actually use correct F values. And so the finishing touch of this problem is to check the fully turbulent assumption and reiterate with a newly calculated F value if it's not.
Isn't that Reynolds number based on the velocity?
Yeah. And so we need to go through it a third time maybe. But it's a pretty close velocity. Because remember, it wasn't that far from being fully turbulent. If you look at the percent difference, I mean, it's probably like a 1 or 2% change in the F value, which is pretty minor. But you're right, that Reynolds number is based on the wrong flow velocity. Yeah. All right, so that's the Nodal method. We found the relative flow rates through pipe 2 and pipe 3. So how would we now use that to find what's the pressure at D? Well, the process for finding the pressure at D is to start with what is the pressure at A, and it's just applying the energy equation. So you find the total head at A, then you find the head at B, then you find the head at C, and then finally at D. Maybe I'll just show you the calculations rather than going through on the whiteboard. Let me just pull them up on the document projector so you can look at that. And it's probably not something that you need to necessarily copy down, but it would be okay just to look at it for a moment. All right, so you find the total head is defined as the sum of the pressure, elevation, and velocity head. And so we find what's the total head at A. In this example problem, they said, what if the pressure at A is 900 kilopascals? And so we find the pressure head term, 91 meters. The elevation at A was 35 meters. You add the velocity that's known at A, and you find the total head is 128 meters. And so the reason why water is moving from A towards B is that there's less energy at B. And how much less energy is there? Well, you subtract the friction losses. And so this is just the energy equation again in the Nodal method format that I showed you earlier. And so you start off with 128 meters of head at A, and between A and B are losing some friction, some frictional losses that turn out to be 13.5 meters. And so now we know the total head at B is 114.88 meters. So we know the head at B. If we wanted to, we could calculate the pressure at B. In this example, it's asking for us to go all the way to D to find the pressure there. And so now we can just say, well, what's the pressure at C? We're going to have to go through one of the routes, not both. In this example, it's showing the friction losses through pipe 2. We could have also done it the friction losses through pipe 3. Either one would have given you the same amount, because remember, that's the whole point of the Nodal method, is that regardless of the route, the head loss is the same. So then we find the total head that's at C, and then how much is the head at D is just going to be applying this again, the energy equation. It'll be the total head that there was at D minus the losses, and so you find out the total head at D. And then to find the pressure, you rearrange the definition of head. It's the pressure, elevation, and velocity head term. Adding in the velocity head. This was the given elevation at D, so the only unknown is the pressure at D. And if you care to work through the remainder of that example, it turns out that the pressure at D is 128.7 kilopascals. But I didn't want to go through the trouble of writing on the board and having you copy it all down when it's just applying the friction loss equation 4 times through those different steps. Yeah?
Right there, the HC minus
Uh-huh.
F over D.
Yeah, yeah.
Is the F over D, is that the C or D?
That's through the pipe that connects C and D. You know, C and D are points, but there are pipes that connect those points. So let me go back to, so it was talking about the pipe 4, the characteristics of pipe 4. So it was the F value for pipe 4, the diameter for pipe 4. Yeah, I use these values. Yeah. It's easy when working with water gems or when working with problems like this to get mixed up with junctions and pipes. You know, is D a pipe or is it a location? Or sometimes we use numbers for locations, but in this case, the question was, you know, which F, L, and D to use. It's the characteristics of the pipe that connects these 2 junctions, D and C. Are there other questions on how to apply that to find the pressure? In some ways, it's related to the homework problem that you did, the second homework problem that you turned in today, where you had to find, once you found the head, then you had to find the pressure at a location. All right. Huh? All right. You've got practice. Okay, so this last thing is that image is from your homework. And sometimes after showing students the example we did in class today, they feel comfortable with it saying, well, yeah, it's obvious what's going to happen if you've got all right, if you've got water that splits and then rejoins, you know, this is pipe 1, this is pipe 2, this is pipe 3, this is pipe 4. Easy. I know how to solve this. But then in the homework problem, it adds in another pipe in the middle. And then all of a sudden it seems like, oh, it was so complicated the first time around when there was 2 pipes. I can only imagine how much more complicated it's going to get when there's a 3rd pipe in the middle. It doesn't get more complicated at all. It's the same thing, where the head through any one of the pipes is the same regardless of the route that you take. And so what I've done is I've summarized the steps that you need to follow for a 3-pipe problem. And they're shown here on the screen, and also if you look at the last page of the notes that I gave you, it's got the same thing identified. You have to begin by guessing an F value for the pipe. And so the most accurate way to do that is just by assuming fully turbulent flow like we talked about today. And then you are going to write the head loss through pipe 1 relative to the head loss through pipe 2, so setting these 2 equal. And so you'll find 1 in terms of 3, and then you're also going to do the same thing relating 1 and 2. 1 and 2 and 1 and 3, and so that all 3 terms of the continuity equation, you're going to have V1 in terms of itself, V2 in terms of V1, V3 in terms of V1, and so that you'll have this equation with just 1 variable in it. And so I think that these steps will make it easier for you to go through that homework problem and be able to solve it. But the one final thing I wanted to emphasize today is the convergence criteria. And you know, you're going to check the fully turbulent flow assumption, and if it's not valid, you're going to go through the whole process again with an F value that's based on the Jane equation, because now you'll know a Reynolds number. Good enough is 1% when it comes to the F value. So compare the original guess F value that you had and your newly check F value that comes out of the Jane equation, and you don't need to redo it again if they're within 1%. I don't have a really straightforward way of applying this in Excel. I mean, certain things along the way, I mean, you can calculate area in Excel and head loss in Excel, but I don't have an automated cut and paste way to solve this problem. Maybe there is, but it didn't jump out at me. I usually do these on paper. Yeah.
On this handout,
Mm-hmm.
on this picture.
Yeah.
explain-
Well, that picture is something that we're going to get to on Thursday. So that's a hardy cross problem that don't worry about that one quite yet. But you can solve the other one, the book problem that it mentions. You can begin on that. All right. Finally, I got a question today about, will you get spreadsheet questions on exams? And the answer is yes, you will. You'll have questions on the exam where I'll let you use a spreadsheet to solve it, but you're not going to be able to use previously solved homework problems. You're going to have to come into the exam with just a blank workbook and start from scratch. You'll also have an equation sheet, and so on your equation sheet, if you want, you can list what are the column titles that you have. Like you'll say, in a 3 reservoir problem, I like to have these columns. You need to remind yourself of what you need to do, and you can write the equations. You can't start with the homework problem and open up that homework problem on the exam to solve the exam question that I'll give you. And then the other thing is I wanted to mention in the quiz, a lot of you were sort of on the right track with the quiz question where I was asking how is the Darcy-Weisbach equation harder to use than Hayes and Williams, or maybe I said how is Hayes and Williams easier than Darcy-Weisbach. Some of you mentioned the difference between Jane and Colebrook, which, the Jane is easier to use than Colebrook because Jane is, it's explicit, whereas Colebrook is implicit, but neither of those equations are used in the Hayes and Williams equation. The correct answer was that the Hayes and Williams equation, friction factor doesn't vary with flow. It's constant. That C value is constant over the range of flow conditions. And so I just wanted to point out that there was, that's a related thing. Colebrook versus Jane is a related dilemma, but the main dilemma is just that the C value doesn't vary over flow function with the Hayes and Williams equation. All right, well, that's it for today. We're going to finish a little bit early, so remember that next time I keep you late. Just to summarize, you've got homework 4 in your hands right now. You can solve problem 42, or get started anyway. And then we're going to go over the material you need to solve the handout problem in class on Thursday.
Do you have a date of our first test?
It should be on the